The last section of Chapter 11 that we want to talk about is Section 3, and it deals with the chi-square test for independence. This is yet another form of a chi-square test. So the key question from your perspective is, how am I going to know when to use this chi-square test as opposed to something else? So let me give you the assumptions that are necessary for this kind of test. First of all, we still have nominal data, just like we do for any chi-square test. Now we have one population, okay? And what we want to know is, for two variables, are they related to each other or not? So the key question is relationship or maybe dependence, okay? Those are used interchangeably, relationship or dependence. The null hypothesis for this kind of question will always be the two variables, whatever they are independent, not related. The alternative is that they are related. And so the differences between this chi-square test and the other ones that we've done before will be primarily in terms of how the null and alternative are set up. Because remember, for the other proportion test, it was always the proportions are equal or they're not equal. Now we're going to be saying the variables are not related or they are related. Okay? So are the variables related or are they not related is what we want to find out. The null says they're not. The alternative says they are. But we only have one population, and we want to know relationship or dependence. That's the key thing to look for as you read your problem. Okay, now we have two groups or categories. And again, the null says they're independent. There's no relationship. The alternative says they are related or dependent. The way we calculate chi-square is the same as it was before. Same formula. We find observed and expected, difference squared over expected, and add it up for all the cells. Our formula for degrees of freedom is now r minus 1 times c minus 1. Now remember, you can use this formula anytime. It's just that the rows will be 2 in the case of the 2 by 2 contingency table, and the columns would also be 2. When we move to more than 2 columns, populations, we still had 2 rows when we were talking about a proportion. Now we're simply talking about categories, of which we can have more than 2 rows, and therefore it's rows minus 1 times columns minus 1. Expected values still have to be at least 5, just like they have been up until now. Okay, here's our formula for expected frequencies, same one we've been using. Row total times column total divided by n. This will be on your formula sheet, so you don't need to memorize it. Just make sure you know how to use it. So our decision rule is similar to what it's been before. If the calculated value of chi-square is greater than the upper-tailed critical value, I'm going to reject the null. Otherwise, I will not reject the null. r minus 1 times c minus 1, remember, is my degrees of freedom. Here's an example. Let's say we're looking at a sample of 200 students. So that means n equals 200. And we're looking at different college level classifications, freshman, sophomore, junior, senior. And we're looking at how many meals that they select on the meal plan, 20 per week, 10 per week, or none. And we're trying to find out, is there a relationship between the classification level or the class standing of the student and how many meals per week they're likely to select, which plan they might want to pick. So remember, n is 200. We only have one sample, but we have 4 class standings and 3 meal plans. So it's a 4 by 3 row table now, which means we're going to have 12 different squared differences to add up to come up with our chi-square value. Okay, so here's the null. Meal plan and class standing are independent. There is no relationship between them. Make sure you write down the names of the 2 variables, not A and B, but whatever they are. Meal plan, class standing. Alternative says meal plan and class standing are dependent. There is a relationship between them. Okay, so as usual, I've got to find my expected values. So I take row total times column total and divide by the n, which is the 200 over in the corner. And that's going to give me expected values that correspond to each cell. My observed values are what I found in the sample that are given to me. Okay, so that part is pretty similar to what we've done before. To find chi-square, remember we now have 4 times 3, 12 different numbers to find the squared difference and divide by expected and add them up. So this is the number that we ended up with for the chi-square value. 0.709. Looks like a pretty small number. And it looks even smaller when we find our critical value. Our critical value is based on 4 minus 1, number of rows minus 1 is 4 minus 1, columns is 3 minus 1, gives me 6 degrees of freedom. So I can go to my chi-square table, look in the row that corresponds to 6 degrees of freedom, and I can find my new chi-square value. Okay, it's going to be different than it was before because I have a bigger table and therefore more degrees of freedom. 6 degrees of freedom is what I'm working with now. So an alpha level of 0.05, 6 degrees of freedom, there's my number, 12.592. Okay, same thing the book got for us, 12.592. So if my calculated value is greater than that, I'm going to reject. Otherwise, I'm going to fail to reject. Well, it doesn't look very close. We only got 0.709, so I don't think my answer is even going to be sensitive to alpha. It doesn't look very close to 12.5 to me. Okay, so here's our decision then. Calculated value, 0.709. Critical value, 12.592. Fail to reject the null, 0% confidence. Does not look like there is any relationship between class standing and which meal plan someone is likely to select. Okay? Remember, for any chi-square test, you want to use your 6 steps. Make sure you remember what those are, and we can plug those in. Let me go through maybe one quick example of that so you can remember how that works. So now what we want to do is go through our 6 steps. Step 1, null hypothesis. The null hypothesis is the 2 variables, whatever they are, class standing and meal plan, are independent, which means not related. The alternative hypothesis says class standing and meal plan are related or are dependent. So I'll use dependent over here. Just use those marks to indicate it's the same thing. Class standing and meal plan are independent, and now they are dependent in the alternative hypothesis. Step 2, remember in this problem I have how many populations? Only 1. So my sample size is going to be the combined sample size for both groups. Okay, here's our data. Our sample size was 200. That's the combined sample for both variables. We had 200 total observations. Alpha was equal to 0.05, excuse me. Okay, so 200 and 0.05 are what we're going to use in the next step here. So n equals 200, alpha equals 0.05. Step 3, this is a chi-square problem, but remember you have to tell me what kind of chi-square problem because we have several kinds. This is the chi-square test for independence. And the way that I know that that's what it is because it's asking me about relationship. I have nominal data, but I only have one population. And I want to know if these 2 variables that we've got are related. That's the question they're asking me. Okay? Nominal data, yeah, we said that. Okay, so we're ready for step 4. We've got to come up with our critical value. Remember, the critical value of chi-square is going to be based on rows minus 1 times columns minus 1 degrees of freedom. In this case, that was equal to 6. I looked in my table at 0.05, and I found that my value was 12.592. So if I get a value greater than that, I'm going to reject. 12.592 is right here. Reject out here on the end. Okay, so I'm ready for step 5. My calculated value of chi-square after I find my expecteds was equal to 0.709, which is way over here, 0.0709. I'm sorry, 0.709. It's still very small. It's going to cause me to then fail to reject in step 6. Fail to reject the null. And because I'm failing to reject the null, I've got 0% confidence. Because I have 0% confidence, I'm going to have no change in policy. And what I'd be saying is, I think that class standing and meal plan are independent. Knowing one doesn't help me to predict the other one. Class standing and meal plan are independent. Okay, so that is my chi-square chapter. That is chapter 11, section 3. We can try one example problem here. Let's see which one we want to try, and then we'll be done. This is, and I'll just kind of get you started to see the 6 steps. I won't go through all the calculations just because it takes a while, but we can give you some time to practice on your own. 1128 is the problem. And again, let me just kind of reiterate this. The way you learn how to do this is by practicing problems. You don't necessarily have to do all of the problem. You just have to do enough of it so that you can make sure you know how to do it. Set it up, figure out what kind of problem it is, and then you can go on to the next problem. So you probably don't have to go all the way through as long as you know what the steps are and what you're doing. Okay, this is problem 1128, and we're on page 398. A large corporation is interested in determining whether a relationship, there's the key word, exists between commuting time of its employees and the level of stress-related problems observed on the job. A study of 116 assembly line workers, that means we've got one sample, and we want to know about relationship. That's how I know it's a chi-square test for independence. Reveals the following. So we have our data. At the 0.01 level of significance, so we have to use that, is there evidence of a significant relationship, there it is again, between commuting time and stress level? Okay, so let's go through. First step, null hypothesis is commuting time and stress are independent. The alternative hypothesis is commuting time and stress are dependent. The value of one affects the value of the other one. Step 2, what size sample do I have? My sample, one sample that I have is, so I just say n equals 116. Don't tell me n1 equals something, n2 equals something, because I only have one, remember? And so alpha equals 0.01, because that's what they told me to do. Step 3, this is a chi-square test for independence. It's a test for independence because they're asking me about relationship and because I have nominal data. I have one population, I have 2 variables. So that's why it is a chi-square test for independence. Step 4, I have to come up with my critical value of chi-square. This is going to come from the table, remember? It's going to be based on rows minus 1. And I have 3 rows. Remember, you don't count the totals. I have 3 rows, and I have 3 columns. So it's a 3 by 3 table is what I'm looking at here. And I can go to my chi-square table then to find that critical value. That critical value is going to be 13.28 in this case. Okay? 13.28 because it's based on how many degrees of freedom? It's going to be 2 and 2, but it's a 0.01 level of alpha, so critical value chi-square equals 0.01, 4 degrees of freedom, and the value was 13.2 is my critical value. Step 5, chi-square. We have to find observed values, which we do the same way we usually do. Row total times column total divided by n for each one of the 9 cells of the table that we have. Make sure all those expected values are at least 5, and then we can calculate chi-square. Chi-square turns out to be 9.83. It's my calculated value of chi-square. It is less than my critical value, which was 13.2. Whoops, 13.2. I got 9.823 right here. So because this value is not out in the rejection region, that's why I'm going to fail to reject the null. Fail to reject HO. Okay, what does that mean? That means I think that the 2 variables, stress level and commuting time, are independent. not related. Knowing one doesn't help me to predict the other one. 0% confidence, no change in policy. However, if I look at these two numbers, I would say, gee, they look kind of close together, 13.2 and 9.83. So my answer is probably going to be sensitive to alpha. So I would say it is sensitive to alpha. Okay? To find out for sure whether that's true or not, all I need to do is go to the row that corresponds to 4 degrees of freedom and look up an alpha level different than 0.01, like 0.05 or 0.10, and see what critical value I get. So let's do that for a minute. We're actually kind of finding the p-value at the same time for this problem, so we can write that down too when we get there. So what I'm doing is I'm looking up my step 5 value, 9.83, in the row that corresponds to 4 degrees of freedom. So it's going to be between 0.025 and 0.05. Okay, because those are the closest values I can find in that table. 0.05, 0.025. So I'm going to write that down. I would say P then must be between 0.025. I'm sorry, let me put it on the other side. 0.025 and 0.05. So I could have 95% confidence in the decision to reject the null, or maybe even as much as 97, but not 99, which is what I asked for. So that's why my answer is sensitive to alpha. The maximum confidence level I could have, we'll say, is 95, and I'm needing more than that to reject at 0.01, which is why I'm failing to reject. Hello. I wanted to give you a little bit of review for the exam. We've got our third exam coming up shortly, and just wanted to give you some ideas of what you might expect there. As usual, we're going to have 10 objective questions on the exam. Those are over assumptions or meaning of what we've been doing, why we're doing it. It's a little harder to tell you about how to prepare for that part, but by now you're getting an idea from the first two exams, I think. The primary material that will be on this third exam will be section 10.5 of that chapter, as well as analysis of variance and chi-square. So section 10.5 and chapter 11 is the chapter material. We'll be looking at one-way analysis of variance. Let me give you a little bit of a review for that. Analysis of variance, remember you have interval or ratio data. You have several populations. The basic question you're trying to answer is, are the means the same? The null hypothesis says the means are all equal. The alternative says the means are not equal. Okay? You're going to be looking at a set of data and developing a summary table to figure out how much of the variation is due to the treatment and how much is due to something else, which you can call error or unexplained. There's a variety of words, remember, we can use there. The greater the amount of variation that is explained by the treatment, the more likely it is we can reject the null. So a high value of f is going to cause me to reject the null. Okay? Define degrees of freedom, remember, for analysis of variance, you have C minus 1, which corresponds to the columns. You have n minus 1, which corresponds to the total number of observations minus 1. And then you have n minus c, which is that total number of observations minus the number of columns. One of the things you want to be familiar with in this section is how are the values in the summary table related to each other. I might give you a partially completed table and have you finish the rest of the table and tell me what decision you would make. You need to know what to do with that summary table. What do you add and subtract? What do you multiply or divide to find the other missing values so that you don't have to spend all your time doing calculation. You can spend your time telling me what it means, which is what I want you to do. Okay? We have, after we do analysis of variance, remember, if we reject the null, and only if we reject the null, do we have to do the Tukey-Kramer procedure. That is where you're testing to find out which of the means are in fact different. Because remember, when you reject the null, you don't know which ones are different. You only know there is a difference. So you're going to find out by using that other procedure which ones are in fact different. Okay? We're going to give you a chance to do some of that work on the computer. The analysis of variance primarily will be done on the computer, and we'll give you a problem as a portion of your exam that you will turn in with that exam to cover that material. You do need to know about the structure of that ANOVA table, and you need to know about chi-square problems. Remember, chi-square is different because we have nominal data, not interval or ratio like we do with the analysis of variance. Analysis of variance has normal population distributions, several populations, independent random samples, equal variances. Those are the assumptions. When I go to analysis of variance, I don't even need a normal population distribution. I need nominal data. And all I'm really asking about is, if it's a test for independence, are these two variables related? Or if it is a proportion test, is there a difference in the proportions? Okay? Remember, if it's a chi-square problem, it has to be difference. It can't be greater than or less than one-tailed test. It has to be a difference that I'm testing for. Okay, remember the test for independence has one population and two variables. The proportion tests have several populations and one variable that we're testing for. So that's one of the key differences as well. Okay, hope you do well on your exam, and we will pick up with Chapter 12 next time, which is regression and correlation.